Hello folks, we're back with more conservative fields. Last time we saw the definition of conservative fields and how they make it easy for us to calculate work integrals because they are independent. The value of the work integral is independent of the curve. What only matters is the endpoints. Now one issue that we had was, how do we decide, given the formula of a force field, or or velocity field for that matter, how do we decide if it is conservative or not? Okay, so we're going to look at the component test for conservative fields. Again, the setup is the same. We have a field that is mi plus nj plus pk. Remember, m and n and p are all multivariable functions here. Okay, they're not constants. How do we decide if this field is going to be conservative or not? Well, remember many weeks ago when we were doing partial derivatives, we saw that for nice functions, right, for nice functions, we had the derivative f sub xy is the same thing as f sub yx. My bad, sorry. F sub yx. So this means that what I mean is the following. If you take the derivative of f with respect to x first, then you take the second derivative with respect to y, that usually ends up, for nice functions, that ends up as the same as taking the derivative with respect to y first, then taking the derivative with respect to x. So we're going to use this idea. If we have a vector field f on a simply connected domain, and m and n and p have continuous first partials, then f is conservative if and only if py is equal to p sub y is equal to n sub z, derivative of p with respect to y is equal to derivative of n with respect to z, and m sub z is equal to p sub x, and n sub x is equal to m sub y. So this might feel like it's a lot to memorize, it's a lot to handle. It really is not, as long as you remember this fact. F of x sub y is equal to f of y sub x, okay? For functions with continuous first partials. Now, f is conservative if and only if there's a potential function, small f, such that its f is equal to gradient of small f. In other words, big F is small f sub xi plus small f sub yj plus small f sub zk, okay? In which case, we automatically deduce that f is going to be conservative if and only if f sub x is going to be equal to m, f sub y is going to be equal to n, and f sub z is equal to p. Once you write this, the theorem is free, okay? Why? Because what do we get? Well, p sub y is the same thing as f sub zy. Well, I would expect that to be the same thing as f sub yz, but what is f sub y? F sub y is n, so n sub z as desired, right? P sub y is equal to n sub z. Now let's look at this one, okay? This one says m sub z, but what is m? M is the same thing as f sub x, so n sub z is f sub xz. That's the same thing as f sub zx. Well, what was f sub z? F sub z was p, so this is p sub x. And finally, n sub x, what was n? N was equal to f sub y, all right? And so n sub x is going to be the same thing as f sub yx, and that's going to be f sub xy. And what was f sub x? That was m, so that's m sub y. So if you don't memorize it this way, okay, if you don't, and just memorize the fact that m is just f sub x, n is f sub y, and p is f sub z, then just turning the derivatives over, right, the partials, changing the order of the partials, you get the theorem for free, okay? So this gives us an immediate way to check whether a given vector field is conservative, okay, before we invest our energy into finding the potential function for it, okay? So you always want to check whether the given field is conservative first before you put energy into deciding what its potential field small f is. So here's an example that we're going to work on with today. I picked a very, very simple function. I picked a very, very simple vector field function. F is equal to 1 plus zi plus 2yj and plus xk. So what the question is this vector field conservative? So what do we need? We need m sub y, okay? In other words, f sub xy, okay, to be equal to f sub yx. So I want m sub y to be equal to n sub x. Well, m sub y, derivative of this with respect to y would be just 0. And derivative of this with respect to x will be 0. So 0 is equal to 0. Check. That's good. Okay. And next thing we want to check is m sub z. So m sub z here would be 1. Okay. That is f sub xc. I want that to be the same thing as f sub zx. In other words, I want that to be f sub z is p. So p sub x. Okay. Look at p sub x. That's again 1. So 1 equals 1. Great. And finally, we do n sub z. Now, n was f sub y. So n sub z would be f sub yz. I want that to be the same thing as f sub zy. So I want to take derivative of this with respect to y, and both are 0, right? So good. All of the conditions are satisfied, and we have verified the fact that this vector field is indeed conservative. So the question is, let's say I'm gonna calculate some work integrals now between 2 points, okay? Or I'm gonna calculate some flow integrals, okay? Now, how would I find the potential function, right? If we can find the potential function, it's all gonna be very easy. So we're gonna find the potential function for this. This method works in general, or methods like this work in general. So we're gonna again take the same function. We're gonna again take the same function, f equals 1 plus zi plus 2yj plus x sub k. And we're going to ask ourselves, what is this small f? In other words, when is f equal to gradient small f? I know f is conservative, so there is such a potential function, but which one it is? Which one is it? Sorry. So what we know is, since I know that there is a function such that f is equal to the gradient of f, well, df dx is 1 plus z, okay? So integrating both sides with respect to x, I would get f is equal to the integral of 1 plus z with respect to dx, okay, 1 plus z dx. So that's going to give me, when I do it with respect to x, of course, z is a constant, so I get x plus xz plus a function of y and z. I'm going to call that g. Why do we get a function of y and z? Because we know that we are dealing with a 3-variable function, okay? And now we can't have any more x terms that have x in them, because if we did, we would get derivatives of them would be non-zero. But any function that is just in terms of y and z, their derivative, its derivative would be 0. So if you take derivative of this side, derivative of this guy is 0 with respect to x. This would be 1, this would be x, so this would be 1, this would be z, so you get 1 plus z. So this behaves like the constant. So you would want to write xz plus x plus xz plus a constant, but constant in terms of who? Constant in terms of x. Constant in terms of x means it's a function of the other 2 variables, y and z, okay? Now, the other thing that we know is, well, if I take the derivative of f with respect to y, I'm supposed to get the second term, 2y. So 2y is equal to the df dy. Okay. Well, great. Great. Now, because we know f is equal to this guy, okay, let's take the derivative with respect to y. We get this guy is 0. This guy is 0. So whatever this guy is, 2y has to be equal to the derivative of g with respect to y. That's the only term that's left. Okay, so from here, I'm going to get g of yz is going to be just the integral of 2y dy. So it's going to be y squared. That's what I get from the integral of 2y squared over 2, which is y squared, plus a constant. A constant in terms of who? A constant now in terms of z. That's the only variable left, right? Because anything in terms of z, when I take derivative of it with respect to y, that would give me 0. So far, I've reduced the problem into the following question. I have, okay, I have f was equal to x plus xz plus, what was it? G of xy, but we decided that g of xy is y squared plus hc, so let me just label that, okay? This is g of xy, what we used to call g of xy, okay? So all we need to do this now is decide who h of z is. Well, guess what? We're going to use the third partial for that. We know that the derivative of f with respect to z is x, so we know the f dz is x. But if you take the derivative of this with respect to z, well, this is going to be 0, this is going to be x, this is going to be 0, and this is going to be dh dz. So if that equals x, right, cancel the x from both sides, you get that dh dz is equal to 0, which means h of z is just any constant c, okay, any constant c. So we get that the potential field could be x plus xc plus y squared plus c, where c is a constant. So the answer is, of course, infinitely many potential functions for this given vector field. For actually any given vector field, there's going to be infinitely many potential functions. Why? Because the derivative of a constant, real number, is always 0, right? That's always going to be 0. So you could do just this, or plus 1, or minus 1, or plus 2, and so on. They would all give you the same answer. Now, in terms, is this going to bother us? No, not one bit. It's just like antiderivatives and integrals we had in calculus 1. When we are evaluating, right, this between 2 points, the c does not matter. The c just drops out. So let's exactly do that. How would we integrate? How would we do these integrals? We haven't seen an example around the loop. Let's see an example around the loop. Okay. So I am going to use the same example. We are going to try to find the work done by f. It's the same vector field, 1 plus z I plus 2yj plus xk, and we chose on this curve r of t cosine ti plus sine tj plus k, where t is between 0 and 2 pi. Now I'm going to do it two ways. I'm going to do the fundamental theorem of line integrals way. So it's going to be again faster than light. It's going to be very quick. We know, we just calculated this, the same vector field. We know that f is equal to gradient small f, where small f, we can take it, I'll just drop out the constant, doesn't matter anyways when evaluating integrals. Small f is equal to x plus xc plus y squared, okay? This, of course, means since it's a gradient field, big F is a conservative field. Now, what we note is r of 0, plug in r of 0 into this function, you get the point 1, 0, 1, okay? And plug in 2 pi, you get the same thing. So we have a loop, okay? And we know that for conservative fields, the work done around the loop is 0, nothing, okay? It's nothing. So we didn't have to do any calculations at all just because we knew it was conservative, okay? And we know, we knew it was conservative just taking the components. We didn't have to find small f. And because the starting point and end point is the same, the work integral has to be 0, done. That's the FTL way. Now, in the old way, we would have to do, to calculate f dot dr around the curve, we'd have to do 0 to pi f of dr dt, okay? So for f, x is going to come from here, right? This guy is going to be x. This guy is going to be y. This guy, there's 1 here. 1 is going to be z. Okay? So what we could do is then if 1 plus z is just going to be 2 because z is 1. Okay? And 2y, well, y is sine, so that is going to be 2 sine t. Okay? Plus xk, x is again cosine t, so f is this vector, times derivative of r is going to be minus sine, cosine, and derivative of 1 is 0, so this guy dt. So you do the dot product, we're going to get minus 2 sine t cosine t, and this guy is of course 0, so it doesn't contribute, okay? And if we go to evaluate now, the integral of this is going to be 2 cosine t. The integral of this is going to be sine squared, 2 sine squared over 2. Notice that cosine t is the derivative of sine, so you could do a substitution if you don't see it immediately. It's going to be sine squared over t. We evaluate from 0 to 2 pi. Again, we get 2 minus 2, which is 0, which is supposed to be the right answer, right? So instead of doing all this dot product, derivative, and whatnot, just checking the component terms and realizing that this is a loop and the answer is 0, that's just a much, much faster way to handle it. Okay, now I want to talk a little bit about exact differential forms. Remember, we also reduced the work and flow integrals to this type, right? m.dx plus m.dy plus p.dz when f is equal to m, I, and j plus pk. Okay, so we're going to make a definition. An expression of the form m dx plus n dy plus b dz is a differential form. A differentiable form is exact on a domain D if m dx plus n dy plus p dz is equal to df dx, df dy dy, df dz dz, and I'm going to call that as df, okay, this whole thing as df. Now, why is this notation coming? Why are we using this notation? Because, well, we know that the answer, since this is the work integral, okay, well, and f is equal to these components, this guy is going to be conservative when there's a potential field f for it. Well, what does it mean if there's a potential field for f for it? Well, m is equal to df dx, so m.dx becomes df dx times dx. N is equal to df dy, so n times dy is equal to df dy, and p is equal to df dz, so p dz becomes df dz dz, okay? And remember, the work integral of f dot dr comes out to be just small f, so that's why we're using this form integral of df. When we take the integral of this, it's the same thing as notation-wise, it's the same thing as taking the integral of df. And what's the integral of df? Well, it is f, okay? For some scalar function f. By a scalar function f, of course, we mean it's not a vector function, it just has x's and y's and z's in it, okay? So now we can do the component test for exact differential forms, okay? So we're going to have the m sub dx plus m sub dy plus p sub p dz is going to be exact if and only if f is conservative. In other words, f has a potential field small f. So in that case, we can apply the exact the component test to exact forms. The differentiable form m dx plus n dy plus dz is exact on a simply connected domain if and only if, well, it's the same thing we had just a few minutes ago. dp dy is equal to dn dz, dm dz is equal to dp dx, and dn dx is dm dy, okay? And this, of course, if we have this for that exact differential form, it means the force field m I plus nj plus pk is conservative. So it's basically the exact same test, but for these differential forms. All right, that's going to be it for today. I hope to see you later on. Take care. Bye-bye.